9 o'clock.
Yeah, especially with how late the nights have been.
Some arrive later.
It took longer to come over in an Uber yesterday than it did to just walk
Really?
from
Oh.
the house.
Oh, yeah?
But it's a 20 minutes.
Walk.
So got a little good exercise this morning. It'll take me a good half hour to cool off.
Yeah, I wish I could walk actually. I'm just beginning to know the direction. And I was thinking about that this morning as I came into that. I thought, oh, see, I'm now finally knowing where I'm going.
Oh, well, the thing is that I have no time to come and do sightseeing or anything these days. So I just lay of the land. I know where the Vic is, and I know my neighborhood.
And you came from where?
I live in the state of Washington, in the United States. Most people don't know my town originally, but Seattle
It's
is
popular.
yeah,
The capital.
exactly. So Seattle is kind of closer to the ocean, of course, and I'm about 3 hours east and slightly south of Seattle. That's our big city that we go to when we go shopping.
Okay.
Have a weekend getaway.
Seattle is quite a quiet place, I think.
Yeah, it is. It is. And then the other fairly well-known city in the state of Washington is Spokane. And Spokane is a little bit closer to us. It's about an hour and a half to almost 2 hours.
So how do you find it being in Washington?
Oh, this is amazing. I love the international experience. I've loved to travel. I've loved to visit places hundreds of years ago. The United States is a young, the United States, of course, since I lived there until I made it easy for me to be able to do things and know how to do things. Just even figuring out how to get to fishing school and where to find a doctor, things like that have been really challenging. But I have to say, I think the medical care process and system in general is much better. I really like it.
Definitely. Huh?
Better in
Yeah.
most European countries.
Yeah. Yeah.
Except the UK.
Yeah.
Yeah.
All right.
I hear that a lot.
Yeah.
Is that really true? Like,
They come in France too.
Yeah.
Yeah. It's true.
It's not bad, but it's not as good.
okay.
No, and also it's very expensive.
Well,
This
see,
is
that's
the
how
other.
the U.S. is as well. It's incredibly expensive. But Austria is, I don't know how
But
to
the
do
US
it.
is completely private insurance, if any at all.
I know they've just got the socialist insurance. So
that's good.
Obamacare is what the trademark is for it. And so there's several, it's actually state sponsored. So each state has kind of come up with a scheme, but many states have gone in in partnership. And depending on the price of what you pay for the premium, you pick the way to apply it. And then it's heavily accessed. The United States gets a major fortunes lawsuit because the cost of lawsuits and files in the industry.
I think you hit the nail on the head. That's what I always say about Pennsylvania. Is that the problem in the United States? Care system, how expensive it is for lawsuits. So
The
for
medical insurance was largely
So, yeah, it's okay. Good. Okay. So
and in practice, and after
the first one is still missing.
the doctor has to do anything.
So we will ask right.
You can order for
Yeah,
10,
I will ask. Okay.
but you actually only needs 3.
Right, exactly.
But you're going to order for 10 to avoid loss.
That's exactly what he wants us to instruct.
So that nobody will say, why didn't you also do this one? And he says, because maybe it's not going to happen. Are you sure? And so each times, because when they ordered this person,
So when you this one is here.
okay, so
So
this
the
guy's
only
here
one is missing the first one.
in the morning.
In the morning.
Very first.
And we have to ask.
Yeah. Ask. Yes. Yeah. Maybe. The person is here. Please. Good morning, everybody. Just before starting the session, the first presentation is missing. So please, if Mr. or Miss Neog is here, the presentation about CTBT for UN 2030, Empowering Diplomacy Through Science in South Asia. If the person is here, or you know she's here, please come to the desk to give the presentation. Thank you. If not, we start with the second.
There's no response.
So it seems there is no response, so we will start with the second presentation and come back in case.
Or maybe we ask people at the back to please come forward so we can all kind of see ourselves.
And
isn't
I,
it?
if I could make a recommendation, I think we need to start it at 9:15,
Okay.
because people will be using the schedule.
You think?
There's 2 of us who's presenting, so
2 of us?
Okay.
I think it's
Maybe we
important to
can
stick
wait.
with the schedule. So if our first presentation is a no-show, we'll start the second presentation at 9:15 for others that may want to come in and see it.
Yeah, thanks.
okay. So,
No. Please wait.
okay.
Yeah.
To 9:15,
So
for the second
9:15.
presentation, right?
Yes.
Okay.
Yeah. Oops.
youth thing we're kicking off,
All right.
and then I won't have to leave.
No problem. Great. Cheers.
provided, they don't have the, yeah.
So we let her start, isn't it? So that in case they come back, we'll have time. Okay. Good morning once again, ladies and gentlemen. Now we'll have to start. We just discovered the first speakers walked in a while back, and but while they're trying to get settled and perhaps reincorporated, we'll take on with the second presentation this morning, which is CTBT or IMS contribution to SDG 14, Life Underwater, by Retno Dewi from the Indonesian Agency for Meteorology, Climatology, and Geophysics.
Yeah.
Thank you.
Thank you.
Are you aware of the time?
What?
You
Yeah,
know.
15 minutes, right?
Yeah.
Yeah, okay.
It's presentation and
Yeah,
for questions.
okay, thank you. First of all, this is not my name, it's my friend's name. Ilya Kursenko, he is from Russia. We're supposed to have the presentation in together, 6 minutes each. So I think I'm gonna take his part. So what we did is we tried to use hydroacoustic in the Indian Ocean to, let's say, contribute to work on the SDG. So those are the objectives. We wanted to analyze hydroacoustic data from this period in order to identify the source of events and to interpret those results as SDG 14's goal. So as an introduction, you already know that the CTBT has 4 technologies: the seismic station, infrasound station, and hydroacoustic, which is combined with the radionuclides element in order to verify the compliance, whether a nuclear test has been conducted or not. Well, I think you know where the Indian Ocean is, so I'm not going to spend too much time on that. So basically, there is very few research on that area, so that is one of the that motivates us to do this work. Background on CTBT and SDG. So there are 4 main points related to SDG and CTBT. So it's the climate action, the tsunami warning system, which, by the way, was signed by our country, Madagascar, I think two months ago. Again, there is the volcano monitoring, and the last one is the 14th goal of the SDG, life below water. Ilya and I are like 8,000 away from each other, but we tried to find a way to work together in order to, let's say, promote the CTBT in terms of life below water. So, material and method. The white triangles represents the hydroacoustic station, HO1, 4, and 8. The red ones are seismic stations. In order to locate an event, 3 stations are needed at least. So we had to combine, in some cases, we had to combine those 2 technologies in order to locate the event. Event detections. How do we know where and when happened the event? So during the National Data Center training that we had, we used a PMCC software that is provided by the CTBTO to detect events. Next is the visualization. We used a very basic research, and in order to get what's going on, what has been detected, we used the DIVA software to locate it. The last part of the methodology is to locate the event itself, and GeoTool was used for that. As you can see, this one is HO1, HO4, and HO8. Once the event has been detected from each of the seismic stations, then location is possible using GeoTool. So what did we find so far? Again, the idea is to promote the CTBT through its ability to contribute on SDG. So first of all, those are detections that we've been working on. It was on May, November, and December from each of the 3 stations. Why these dates? Because we were looking for life below water, earthquakes, and tsunami. So if we zoom in, you can see that each stations, for HO1, for example, the events are detected in this azimuth between 150 and 200. This is for HO1. For HO4, there are 2 main detection, one in here and one in here. So we try to identify what are those sources, where are they coming from. This is for HO8, actually. You can see these lines on the azimuth 25 and also in this azimuth. So to summarize what we've seen so far, those are the statistic detections that has been involved in this study. This is for HO1. As you can see, the detections are, most of them are coming from that direction. And for HO4, most of the detections are coming from that azimuth. So we are trying to explain why the stations are detecting those events. So what did we find? First of all, earthquakes. It is part of life below water. Most of the events that are detected from those 3 stations are in the ocean ridge, as you can see, and from Indonesia, this area. So on the right side, you can see that the station HO4, most of the events are from that direction. And it's most likely from that region. So in terms of SDG, what did we find, like volcano or tsunami? So I've been looking at the detection, and there was those lines. We tried to identify why do we have those, let's say, unusual pattern. So what we did is, me and Ilya was looking at the spectrogram of this event, and if we zoom in, then you can see that there is this signal with a periodical period that is coming toward let's say not periodical, but there are those waves that are coming toward the stations, and they were detected from each hydroacoustic stations, and those are energy that are collected after the spectrogram analysis. So we tried to identify what was this. So what we find is that this was the volcano eruption in Krakatau last December 20 to 23. So using these hydroacoustic stations and those seismic stations, we were able to identify an event that is far, far away from HO4. And the wave propagates from that region until these hydroacoustic stations. And on the top right, you can see that the land was collapsing into the water that propagates in the Indian Ocean. So this one is just showing us that the waves are coming from the same azimuth. This helped to identify from which source the event was coming. In terms of cyclone, if the events are close enough to a hydroacoustic station, then it can be detected. So I think my friend Ilya is already here, so I will invite him to come on the stage and to take part of the speech.
Thank you very much, Joanna. Good morning, everyone. Joanna, as you know, is from Madagascar, and he's a geoscientist, and he's in the youth group. And I'm from Russia. I study international relations, and I'm also in the youth group. And when we were at the General Assembly in New York, we came up with the idea we definitely need to do a project together to bring science and diplomacy together, because on words, we do talk a lot about the need of a better dialogue between scientists and diplomats, and also turning these negotiations into the public, delivering them to the public. Though we want to prove our words on deeds, and this project is our example of how diplomacy and science could come together when just 2 young people from absolutely different regions of the world come together. And it's very hot in Vienna. Yesterday I was walking with my friend, and I understood that climate change is a terrible thing, and we need to reduce the temperature down and do everything possible for that. So we concluded our project with the whales yet not found. And it really depends upon them how they flow into the range of stations that could capture them. So our project is still ongoing, and we do look forward to the results. particularly because the next part of the project would focus on whales particularly and on the CTBTO and SDG cooperation in this area. So if anyone is interested in learning more about this project, please do reach out to us. We'd be very happy to share with you. And now we have prepared a very short activity for our listeners. And I brought these 5 pins from Russia that turned out to be exactly the same as the CTBTO prepared, though we didn't know anything about their plans. So please answer a couple of questions, and we would definitely award those who participate. This station that you see in the corner, what kind of station is it? Who could remember? Please just raise your hand and say, what type of a station is it? Hydroacoustic, or infrasound, or seismic? Yeah. You get Yes, please, Joanna. Thank you. Okay, now it's a more challenging question. Please guess what country of the world this seismic station is located at. We've covered the North America on purpose because that's how PowerPoints work. We couldn't fit it into. But it's somewhere uncovered. So the first 4 closest guesses would get the awards, and then we find out what station is it. Yeah? Chile? No. Indonesia? No. Mongolia? Let's see. If no, Kazakhstan? Okay. Warmer? No. Cold? Australia? No. Mongolia? Cold. Kazakhstan? Really warm. Very warm. I think you all are doing very well guessing. So just, yeah. Okay. So let's award somebody who said Kazakhstan first. Who was it? And then just Middle East. So it's in the Middle East. Name the countries of the Middle East. Iraq, close. Very, almost like hot. Iran? Yes. Yes, it's in Iran. So please, Iraq, Iran, and Jordan, you get the pins. Yes. And to Iraq, Iran, and Jordan. So we thank you for your attention, and we are ready to answer any questions that you have. Thank you very much.
Sorry. Okay, just one question. We've actually run over time. Thank you.
Thank you for that. And sorry, I have a question to my colleague from Madagascar. Looking at the hydroacoustic signal, and if you would be close enough, do you think you would be able to assess the volume of the landslide based on some empirical relation with amplitude, etc.? So do you think that would be possible at one stage? Thank you.
So to get the volume of the landslide from hydroacoustic station, I would say further research will be needed for that. Since we just started this project like 6 months, getting used to the data, how to process them is like a mess for me because I am a seismologist. And anyway, I am sure that I can go toward that questions and looking forward to, yeah.
Okay, thank you very much. Sorry, we can't take any more. I'm really sorry about that.
Just a comment about the question, the previous question.
In 5 seconds.
Yes, so the hydroacoustic sensors are sitting in the sulfur channel, which is essentially a high-pass filter. So it's sensitive to high frequencies that get trapped. High frequencies, I mean 3 hertz and above, that get trapped in the sulfur channel. I imagine that such a large landslide would be very low frequency. So I would be, yeah.
Thank you.
Thank you.
Thank you.
Thank you.
So we'll just go on to the presentation on feasibility assessment for geothermal potential in Las Tranqueiras, Venezuela. We'll take the very first one last. So that's going to come after the others. And we are trying to catch up on time. So if you can save us time, that would be fantastic.
Good. Good morning. I will talk to you this morning about a feasibility assessment in Las Trincheras, Mariara, Venezuela. I would like you for a moment to imagine that the largest oil reserve country goes into geothermal energies. And I think that you might already heard that Venezuela has about 3,100 millions of 3 millions of barrels. And at this stage, the country would like to move forward into more sustainable developments as geothermal. Here we can look at the consumption of energy of the whole country. The whole country consumes about 70,000 megawatts. And we would like to take the study further in the 2 most industrialized cities of the country, which hold about 2 million people and would have an energy consumption of 312 megawatts. Unfortunately, this amount of energy can't be provided by just one element of a geothermal system, but the diversification of these energies would help to decrease the amount of energy consumed by the thermoelectric. Therefore, we would reduce the fossil fuel consumption in the country. If we compare this information with, for example, an important project here in Europe, the Munich project in Germany, for Venezuela, we would need, in a frame of reference, about 6.25 million geothermal capacity. Then here we can look at a worldwide map of areas where energy can be, geothermal energies can be exploited. And Venezuela, luckily, is placed in an area that high temperatures could be expected. If we look at to the right-hand side, we can see a map of Venezuela and the hot spring distribution across the whole country. These studies were taken in the 1983 by Frank Urbani, and basically what he did was to map and to characterize the waters of these hot springs across the country. So the mechanism that we would like to use for this to be worked out is to take use of rainy water that would reach higher depths, uprising, and then reaching higher depths, it would increase temperature for these waters that when they uprise, we are able to take this energy for these waters for energy. Here are the 2 goals that we would look at in the frame of this project. One is related to affordable and clean energies, and the other one is related to sustainable cities and communities. For clean, affordable and clean energies, we would raise the awareness of renewable energies or alternatives in an oil-culture country. The areas that would benefit from clean energies would be the 2 most industrialized cities across the country. And sustainable cities, for example, in this area, we would be able to understand the geological setting of the city and lowering the risk by understanding the seismological hazard in the area, as well as we could help in the project to understand better the hazard for microzonation and therefore obtain the goal of sustainable cities. For FUNVISIS, which is the institution that I work for in Venezuela, we would benefit from learning from the seismic activity in Valencia and Maracay cities and try to relate this to a geothermal system or source and lower the seismological hazard. CTBTO would learn from this work the studies, and we will enlarge the analysis related to nanoseismicity with pattern recognition algorithms, event characterization, and geological characterization of faults and fractures. Here we can have a look on the maps that of the city. Valencia and Maracay are in two main capital cities, and in this map we can see geological units as this unit over here would be a metagranite unit from the Cordillera the coast range, and we would expect to look at essentially temperatures of 48.5 Celsius in surface, just from hot springs. So if we try to extrapolate that in a higher gradient, we would expect higher temperatures at depth. Therefore, the cities would be able to benefit from these studies. Here is the recent seismic activity in the area. About 800 events have taken place across, and 2 million people live in these two cities. So if we can see, the seismic activity, even though it's low intensity, has been very high frequency in the area. This is 1 year of events from April 1918 and to April 2019. Here we can see the distribution of that seismicity in 1 year, and we can look at that. We have had 3 main events with 4.6, 4.7, and 5.2 momentum magnitude. And this would show in reference how these magnitudes could be varied and how intense and frequent have been the activity. Here is the proposed flow that we have for this project. The initial phase of our project is related to gather the historical data available, and with this have come out the temperature, the chemistry, geochemistry that have been geological mapping, hydrogeology, and all the historical reports that are available. For the next phase, second phase, we would like to go through relocalization and try to look at the errors between the relocalization errors between using 2 techniques would be Hyperline and iLux, two software from CTBTO. Try to apply pattern recognition analysis to our data. Then after we have all this seismicity located, we can define a fault plane relating this to in depth and start planning a survey so we can have a look at this. Our next phase, our third phase, would be basically integrating all these studies. It would be related to laboratory tests for thermal conductivity, integration of seismicity, seismic electromagnetics, and geology, as well as that have been in the area historically. We would like to implement technicals like brightness temperature to identify surface temperature, and finally, integrate this information in one unique report that would be delivered. Thank you very much for your time. Thank you.
Thank you very much for that interesting talk. Please,
Don't run away.
if there are any questions. Sorry. Before leaving. So we ask the floor if there are any questions, please.
Yes.
Yeah, mine is very simple. Now, just from the temperature of the hot springs, have you tried to recalculate the reservoir temperatures? Obviously, you may not have an answer, but you need to involve geochemists or reservoir engineers. Otherwise, you may invest a lot of funding from geophysics, and yet your reservoir is not as good.
Yes, recently I have learned that isotope studies would help to track the historical path of this water and understand the recharge of the system. So it has, yes, we have considered this, yeah.
Thank you. Is there any second question? No? Okay. Thank you very much. So we move to next presentation by Mr. Retno Dewi, a hazard mitigation analysis of the Anak Krakatau eruption and its tsunami from December 2018.
Good morning, ladies and gentlemen. My name is Kurniati Retno Dewi. I'm from Meteorology, Climatology, and Geophysics Agency of Indonesia, or usually called BMKG. Today, I will present about hazard mitigation analysis of the Gunung Anak Krakatau eruption and its tsunami 22 December 2018. This is the real footage when tsunami suddenly hit an event music in Tanjung Lesung, Banten on December 22. I think it's fresh. Okay, this is the outline. First, history of ancient Krakatau. Second, Gunung Anak Krakatau presence. Third, eruption of Gunung Anak Krakatau, December 22. Four, BMKG analysis. 5, conclusion. And 6, recommendation. I will explain about flash of Krakatau history. Krakatau is between the island of Java and Sumatra. Krakatau history is divided into 3 periods. First period is pre-Krakatau history, consists of composite volcano and formation of 416 Masehi form caldera. And second period is Krakatau history. This volcano eruption divide the Krakatau into 3 islands, namely are Krakata, Danan, and Perbuatan. And third period is catastrophic eruption in 1883. It's a very big eruption. The eruption is heard up to a quarter of the world. As we know, in 1883, there was almost 9 magnitude eruption as seen in the graph comparison of the moment magnitude and corresponding energy release. Starting in 1927, a volcano appeared to be known as Gunung Anak Krakatau from the ancient caldera region. This is the Sertung Island, Panjang Island, Rakata Island, and this is the center is Gunung Anak Krakatau. Okay. On the left picture, Gunung Anak Krakatau was in the constructive phase or building a large body. On the right picture, Gunung Anak Krakatau was in destructive phase. We can see from these 2 pictures, there is only a part left after the landslide. And this is Sunda Strait tsunami timeline, which I divide into 4 big important parts. First part, on the yellow color, is the part about early warning high waves in the Sunda Strait from BMKG, and the status of Gunung Anak Krakatau was level 2 alert from Geological Agency of Indonesia. And second part is, on the red color is Gunung Anak Krakatau eruption and vibration recorded by BMKG sensors but does not process automatically. Third part contains the activity of BMKG analysis, which divide 3 parts on the green color. And the last part, it tells you about a press conference that BMKG has done. BMKG said that the tsunami had occurred was not caused by a tectonic earthquake and prevention center on Gunung Anak Krakatau. This is the analysis of the volcanic activity of the Gunung Krakatau with magnitude 4.9 and depth 0 kilometer. It showed that the eruption caused the landslide, not the earthquake. And seismic record from CGJI station, location in CIGEULIS, West Java, with range 63 kilometers from Gunung Anak Krakatau, and the origin time is 1356 UTC. This is seismic record from CTBTO station in Lembang, Bandung, with range 254.42 kilometers from Gunung Anak Krakatau, and origin time is 1356 30-second UTC. This is seismic record from SBJI station, location in Serang, West Java, with range 77.55 kilometers from Gunung Anak Krakatau, and the origin time is 1356 3-second UTC. There are 4 tight gauges around Gunung Anak Krakatau. Those are tight gauge Marina Jambu, Ciwandan, Stasiun Panjang, and Kota Agung. These are the tight gauge record of Banten area. The mean local wave for Ciwandan is 0.35 meters and Marina Jambu is 0.9 meters. This is tight gauge record of Lampung area. The mean local wave for Stasiun Panjang is 0.36 meters and Stasiun Kota Agung is 0.28 meters. And this is the animation of the tsunami caused by the landslide from Gunung Anak Krakatau. We can see that the vibration is only felt around the volcano and people could not feel the vibration. And this is data on casualties and damages from the National Disaster Management of Indonesia. There are 281 people died, 160 injured, and also damage in the building and infrastructure. And the conclusion, first, with the available data, it seems that the tsunami had hit the Sunda Strait 2018 was caused by the landslide of Gunung Anak Krakatau, not because the earthquake. And second, until now, there are no landslide models that can model tsunami waves. And third, the difference time between the origin time landslide and the arrival time is around 30 minutes. and almost tsunami in Indonesia is a local tsunami. The golden time to evacuate is around 30 minutes. For this reason, we need to carry out additional study, education, and preparedness effort to save people and buildings. And the recommendation for this: first, currently our institution already has a standard operational procedure which is called INATIUS, Indonesia Tsunami Early Warning System, caused by tectonic earthquake. After this, we have to rearrange the standard operational procedure tsunami early warning caused by non-tectonic activity. The second is to increase detection of BMKG seismic sensor in the Sunda Strait. And third, now BMKG collaborate with Geospatial Information Agency and Ministry of Marine and Fishery increase the number of the tsunami warning monitoring around Gunung Anak Krakatau. That's all my presentation. Thank you.
Thank you very much. We'll ask for question, please.
Thank you very much. Maybe just an update, if you allow me. There are tools that are that we can use in modeling landslide tsunami. Whether to have them operationally available 7/24 in an operational environment, that's something else. But I'd like to highlight that there's one publication in 2012 by CGJI et al. That indicates and highlights the potential tsunami due to the rapid destabilization of the volcano and comes up really with good values, quite close. So one thing in the tsunami preparedness and mitigation is actually to take these scenarios on board and draft your evacuation maps, inundation maps according to the scenarios. Now I have a difficult question. I understand if you're not able to answer that. Was such information, such scientific information taken into consideration by your agency prior to this event, since you have an early warning system? Or did it come to your surprise, the scale of the event actually? Thank you.
Because
Do you want the question repeated?
what?
Do you want him to repeat it? Yes, so I think you should repeat the question and slowly, if you please.
Please, slowly.
Okay, I apologize. I wanted to indicate a publication in 2012 that more or less predicts what has happened. So my question was whether such scientific information is being taken into consideration in preparation of your inundation maps for possible hypothetical events such as we had, whether you have been working on evacuation maps, taking such events into consideration. Thank you.
Yes, we have socialization to people about mitigation, and every year, but in this case, because the landslide from Gunung Anak Krakatau does not process automatically in our system, and so we can give the information to people, and this is the recorded in our sensor, but does not process automatically.
Thank you.
Thank you. Is there a second question?
Yeah, it's sort of a follow-up. You mentioned in your slide of a high wave early warning the day before the eruption. So I just want to know, what was the trigger for that high wave early warning? Was it a detection in the rise in the magma chamber or something like that? And that follows up from Ojal's question.
Okay. For the landslide, frequency analysis with the frequency 0.01 until with the slow frequency And for tectonic, the frequency 0.1 until 2 hertz, different frequency.
Thank you. So I think we will move to the next, if there is no any additional question, to the next presentation. Thank you.
Thank you.
So next presentation by Mr. Marchetti, infrasound monitoring of active volcanoes at local and regional scale.
Good morning, everybody. I'm Emanuele Marchetti, and I'm a volcanologist from the University of Firenze. And today I'm going to speak about infrasound and volcanoes, how we monitor volcanoes with infrasound, and the potential use of infrasound also for early warning at larger scale. I would like to acknowledge my co-authors from CEA, Alexis Lepichon and Julia Vergot, from my institute, Maurizio Ripepe and Giorgio Lacanna and Paola Campus, who is now also at CTBTO, Paola Campus and Pierrick Mialle, and Toulouse-Vac, Philippe Rey. So volcanoes are efficient sources of infrasound, and it is very well known since many, many years. But before the 80s, most observations were remote observation performed with barometers. Then, in early 90s, infrasound starts to move to local observation in order to study the dynamics and to apply infrasound for monitoring. Nowadays, there are permanent monitoring systems all around the world on volcanoes with infrasound, so it's getting more and more common. The reason why it's getting more and more common is because it's very efficient for volcano monitoring. Here we see a 2.5 hours record of infrasound of a lava fountain from Etna volcano. Etna volcano is in Italy, is a relatively small volcano, although it's the largest in Europe, and it's producing lava flows, strombolian explosion, as well as lava fountain. Here you see a record which lasts approximately 2.5 hours, and during this phase we have a lava fountain. And when you have a lava fountain from Etna volcano, like the picture that you see here on top, you have problems with air aviation, transportation, streets, and local cities. If we go into the infrasound analysis that is shown below, those dots are basically infrasound detection, so results from infrasound array processing of the data. We see that before getting to the main eruptive phase, which is around 18 here, you have some ongoing activity. And if we zoom into the data, we see that we have single explosion that can be somehow getting closer or larger in time. And with infrasound, unlike seismic, we are really able to track this small amplitude signal repeating in time. So we can use infrasound as an efficient tool to follow the eruptive time history. Another great advantage of infrasound is if you are close enough, it's really precise in terms of source location. This is an example from Stromboli volcano. Stromboli is a very small volcano, very attractive for tourists, but not posing serious risk to huge areas, for example, and is characterized by multiple vents very close to each other. With seismology, it's plenty of seismometers. Stromboli is very well monitored. The density of seismometer is probably the largest of the world. But with seismology, you are not able to detect activity at different vents. With infrasound, you can, and that's been used for research purposes. But another advantage of infrasound, so ahead of waveform analysis, precise source location, is also efficient propagation. Here is a very well-known example by Robin Matosa showing the eruption of Eyjafjallajökull in 2010, which was recorded at source-to-receiver distance of up to 6,000 kilometers. So basically, from infrasound, it's an efficient tool to detect, identify, and locate eruption. And for this reason, there were already some pilot experiments in Ecuador, the ASHE project by Milton Garces from the University of Hawaii, that we used infrasound to detect volcanic explosion from Tungurahua and notify that to the VACs, which are the institute in the world, which are in charge of detecting volcanic eruption and notify that to civil aviation. That project ended, And recently, 10 years ago now, we started a similar project in Italy, which is still ongoing, and I'm going to speak about that today. What we do for Etna is basically use infrasound array processing in real time to identify ongoing volcanic explosion and notify that to civil authority in automatic without any supervision by human being. If we look at this strewn plot, it's showing approximately 8 hours of infrasound records. Each line is 15 minutes, showing a lava fountain. The lava fountain occurs here, where everything gets black, so the signal gets, the amplitude of the signal gets large. If you look at the data, you can see that at the beginning we are almost nothing, and then we start to see some small transients, which get closer in time, here getting closer in time, and then at the end they merge into a sustained, long-lasting, high-amplitude oscillation when the lava fountain develops. We used a very simple parameter that we defined infrasound parameter, that is basically the product between the amplitude of the infrasonic detection and the number of detection. This parameter is very simple because it's a product, but it takes into account both the amplitude of the signal as well as the persistency of the signal. And we could develop some threshold and apply some threshold that are used to notify the change of activity from yellow, basically nothing, ordinary, to orange when the activity starts to increase, to red when the activity is ongoing. We applied that over 8 years of data from 2008 to 2016, and we basically tuned the system during 2011-2013, and since 2015, the system is fully operational. Since then, basically, we could identify all explosive eruption at Etna volcano, and we would have delivered automatic notification with an advance of spanning between few minutes up to few hours before the onset of the volcanic explosion. The mean value is approximately 1 hour between the time instant when we detect the increase of activity and the real explosion ongoing, the real eruption ongoing. This allowed to evaluate, to create a workflow, an information, a communication workflow. So basically from the infrasound system, which is an infrasound array with some processing developed in real time, as soon as the threshold is exceeded, we send information to the scientific community, so to the other institute in Europe, in Italy, as well as the Italian civil protection and local civil protection. However, it also sells immediately the information to the people dealing with the emergency plans, so the majors. And since 2015, this system has been accepted by the Italian civil protection and is fully operational. And it was possible during the last eruptive phases for the majors, so that are in charge of the emergency plan, to activate the plan immediately after the receival of the information delivered automatically with infrasound array analysis. This is applied locally on Etna volcano and has been extremely successful. But we know that infrasound can propagate for thousands of kilometers and can be, so explosive eruption can be recorded at far arrays. Here we have a very well known by a paper by Dabrova showing the plume height, which in volcanology is an estimate of the size, of the magnitude of an eruption, and the distance from the volcano of the infrasound array that detected the event. So basically you see that largest plume, which means larger explosion, larger eruption, are detected far away. However, there are also some red crosses in these plots, which mean that that eruption was undetected by that array at that distance. So it's basically, it's not really, it's not always easy. It's not always easy to detect a volcanic eruption. And this is because the propagation is affecting the signal that we record at the distal array. If we consider the active volcanoes all around the world, there are approximately 1,500 volcanoes which had activity during the last 10,000 years. we see that they are a lot. And if we consider the position of the infrasound arrays of the IMS monitoring system, you see that the volcanoes are color-coded according to the minimum distance to the closest array. So basically, each volcano is at a given distance from an infrasound array, and the mean distance is approximately 900 kilometers, which means 50 minutes. So it's important to try to address two questions. And the questions are, is it possible to record the volcanic eruption? And if yes, if this time is small enough or at least acceptable to deliver some notification that are useful. We studied that during a European project, ARISE, which started in 2012. And is now we are going towards the third ARISE. The main aim of ARISE is to combine multiple techniques to study the atmosphere and small perturbances within the atmosphere, but also one of the aims is to monitor extreme events. And volcanoes are a specific topic for ARISE. This is an example of a volcanic eruption on Etna. It was recorded in 2016, the 21st of May, and it is recorded by ATN array, so a local array, the one that we use for the early warning, as well as in Tunisia at 560 kilometers, Amiata 650 kilometers, and Haute-Provence at more than 1,000 kilometers. Here you have the position of the infrasound arrays that recorded this event. And if you see, the amplitude obviously is much lower. Here the amplitude is multiplied, for example, by a factor of 200 in Haute-Provence. But the waveform is somehow the same. And within ARISE, we investigated the possibility to use this information, a distal array, to provide a notification of the ongoing volcanic eruption. To do that, we have to consider the amplitude and the attenuation. And we use a semi-empirical equation developed and proposed by Alexis Lepichon in 2012, which takes into consideration both the attenuation of the wave in the near field for geometrical spreading, as well in the far field for the propagation within the acoustic duct. And this equation takes into consideration the velocity profile as well as the frequency of the content. Why using this equation? Because it's fast, it's easy, and we need to use something which can be applied in real time, on real-time data. If we apply this equation and we consider a lava fountain from Etna volcano, we see that we are able to reconstruct the amplitude at the source with a quite good reliability. Obviously, there are some discrepancies, like here, for example, but during the main eruptive phase, it's very well constrained. Why to do that? Because at this point, we can apply the same threshold that we defined for the local infrasound array, which are thresholds defined on volcanological parameters, so with a volcanological basis, to far-field observation. And these graphs here shows the IP calculated for the different arrays compared with the volcanic ash advisories issued by Toulouse-Vac. What is shown here is when the volcanic ash advisories were issued, already the information by long-range infrasound would have been useful for the Toulouse-Vac. It is not valid just here, but if we consider 2.5 years of observation for Etna volcano at the Tunisia and Haute-Provence array, we see that this is still valid. So to conclude, local infrasound is getting more and more common in volcano monitoring. It is extremely useful. Volcano observatories are getting more and more used with infrasound. But during favorable propagation conditions, infrasound can be detected at far arrays, and also far arrays can be used for delivering notification in automatic, and the timing is still valuable for the volcanic ash advisory centers. This is valid also for small-scale explosion like Etna. So for larger-scale explosion, it should even be better. Thank you.
Thank you very much. We keep time to have 1 or 2 questions, please.
Yeah, thank you. So speed is very important for disaster management mitigation. So infrasound data is low compared to seismic. So what is the comparative advantage of the infrasound application for disaster management of volcanic eruptions? Thank you.
Thank you for your question. You are perfectly right. Infrasound is lower than seismic, but infrasound can propagate much more than seismic considering volcanic eruption. A VAI4 eruption, like for example, the one in Indonesia in 2014, was recorded with seismometer up to a maximum distance of 100 kilometers. While infrasound of that specific eruption was recorded until up to 5,000 or 6,000 kilometers. So it's slow, but can propagate longer, and is still faster than the decision time taken by local observatory to deliver notification and information to volcanic ash advisory centers.
Thank you. Any other question, please?
Thank you very much. I had a question in terms of cost. What is the, let's say, cost benefit of having infrasound monitoring of volcanoes as compared to having seismic stations and other type of volcanic monitoring devices?
Well, in volcano monitoring, you really need to have multiple kind of observation because volcanic source is really complex. So you have the coupling with the atmosphere when the eruption occurs, but you also have endogenous processes like tremor, which needs seismometer. However, the cost of an infrasound array is similar to a broadband seismic station. And with a single array, you definitely can monitor one volcano just with one infrasound array and even multiple volcanoes if the local geography allows you.
Thank you.
Thank you.
So now we go back to take the very first presentation that should have been taken earlier on by Nyong and Ja, which is on CTBT for UN 2030, Empowering Diplomacy Through Science in South Asia.
Thank you. And apologies that this presentation is taking place now and not the first thing in the morning. I'd like to start by saying our presentation is quite different because it comes from a policy perspective. Ruhi and I have done this project collaboratively. Ms. Ruhi Niog is security and foreign policy specialist, and she works with an Indian think tank, the Institute of Peace and Conflict Studies. Whereas I'm an environment policy and governance specialist, and I currently work with the World Bank. Ruhi and I worked on this project building on a previous collaboration in the field of hydrodiplomacy, where we came to recognize that even in the case of a political deadlock, just also some historical context, India has not signed the CTBT treaty. But we came to realize that even in the case of a political deadlock, there are decisions that need to be made and solutions that need to be found that impact the lives of millions of people. And often these solutions lie in the scientific and technical space. And it's really important to have an interdisciplinary discussion and to dissolve the kind of professional silos that exist to reach these solutions. Our project is titled Empowering Diplomacy Through Science, and we examined the political and historical context, and we find that while India's reservations are very valid, we wanted to put this aside for a moment and actually look at, in this kind of changed global context, what the potential and the benefits are of using the IMS data towards addressing climate change in India. As many of you probably know, India is one of the countries most vulnerable to climate change. 85% of the country's area is prone to some kind of natural hazard or disaster. In 2018, we had floods in Kerala that it's estimated led to a loss of approximately $5 billion, also a loss of lives. And in that, data plays a very important role. India is heavily reliant on the monsoons, and any kind of improved prediction of the monsoons can have benefits for the kind of decisions that farmers make and for the GDP of the country. And we examined a few examples. So for example, scientists now using data from the radionuclide stations can predict the Indian monsoon and the onset of it using radioactivity in the atmosphere 2 months in advance with an error margin of around 3 days, whereas the Indian Met Department can do this 2 to 3 weeks in advance with an error margin of 5 days. And as I was mentioning, this has huge implications for the kind of decisions that get made for preparedness of the monsoon. IMS data also has benefits for tsunami warnings, as well as we have a mission under our climate change aegis called the National Mission for Sustaining the Indian Himalayas. So for that as well, the information is very relevant. Based on all of this, Rui and I found in our project that there is a compelling case for India to consider the use of this IMS data, and it merits a serious discussion. And this discussion would need to bring scientists as well as foreign policy experts together to look at the merits of using this data. And yeah, that in a nutshell is our project. If you all have any political questions, I would request you to direct them to Ruhi and any others. Thank you.
Thank you. Great, thank you. So we'll take questions. It's a slightly different dish from what we've been eating all morning, but absolutely important. So please, can we have questions? You don't care much for policy. Seems like they like you.
Well, we felt a bit like that for the other presentations, where we weren't sure what to ask. So.
Well, could I ask you, do you think there will be a change in India signing the treaty or anything like that?
Rui, do you want to answer this?
I think you should.
Thank you. I don't, of course, speak for the Indian government, but in my estimation, I don't think at this time I see India signing or ratifying the treaty for a whole host of reasons that I'm sure you're all very familiar with. And that will, of course, start with the possibility of the United States ratifying it.
Okay. Thank you very much. Were you putting up your hands? No? Okay. All right. Let's give him a round of applause.
Thank you.
Yes, so we go to the posters. Yeah. Okay, so now we get quick preview of the posters that we have under this. I think we have poster 4, 17, 22, 27, 29, 38, 45, and 47. Now, if there's anybody else who, you might as well just come forward, all those with the posters. Please come forward, sit closer, because you barely have a minute or so to speak. And anybody else who is not listed or mentioned now, please see them at the desk there. It means they've somehow missed you out. And then they can update this list for us. Thank you. Yes, I guess they have a list. So we have poster 4 first, and that's by Ouedraogo. Is he here? Okay, let's skip that. Let's go to poster 17, Martinez.
Hi. Hi, everybody.
Good morning.
Good morning. My name is Alejandra Martinez. I am from Venezuela. The first thing that you have to know here is that tsunamis are a real threat to the Caribbean region. And the IMS of the CTBTO integrated with other networks in the region could constitute a very robust system to minimize this hazard. We have in the Caribbean region an approximate of 12 stations of the 3 technologies of the IMS. And the main objective here is the inclusion of the Caribbean Tsunami Warning Centers and NDCs to the CTBTO disaster warning initiatives. And for me, this is one of the most useful scientific and civil applications of the IMS technologies. And we need to go further, not only with hydroacoustic and seismic monitoring. We need to go further with infrasound technology, like Milton Garces in 2005. Oh, it's finished. We use infrasound for tsunami prediction. So thank you very much. Sorry.
Thank you. Well, I think now she's shown everyone what happens when time runs out. Okay, thank you very much. Poster 22. And that's not controlled by us.
Good morning. My name is Rengin Gök. I'm from Lawrence Livermore National Laboratory. In this poster, we are summarizing our many years of effort in Iraq, collaboration, capacity building, and training. Two major development we have done on the left. On the right, you see the seismic hazard assessment map, pre-ground acceleration 2% in 50 years. And this has been adopted by Building Code Committee and federal government. Now it's being used as modern building codes in seismic provisions of building codes. And the other effort we have ongoing is seismic monitoring development. The red triangles are existing broadband stations. Some of them are sending data to IRIS, openly available. The 3 yellow one is going to be installed this year. And come and see my poster. I have more details. Thank you.
Thank you. Poster 27, please. Missing. So we skip poster 29. Thank you.
Morning, everybody. I'm Shahar from the Netherlands, TU Delft University. We show a compelling example of how an IMS infrasound array can be used to produce a pseudo shake map, even in regions where there aren't any seismometers. We show the example of the Haiti earthquake disaster in 2010. The shake map that you see on the top left is something we generate by back projecting detections from an array. And you see a very good resemblance to the shake map that was generated by the USGS 7 years after the earthquake, as there were no recordings on the island. In post-earthquake disaster scene, this is a game changer. Come by our poster to discuss this. For those who come, there is another pleasant surprise that didn't make it into this 1-minute slide. Thank you.
Okay, and 38.
Hello, I'm Katarina Söderström from Swedish Defence Research Agency. And in Sweden, we have been running sampling stations for particulate radioactivity since the 1950s. And what we have done now is to go back and look in these old archives with all the filters and extract the DNA from the filters, so we can study the biodiversity, both in time during all this period and also in space. We have samples from all over Sweden. So please come and look at our poster and see how many different species we can sample in our filters. Thank you.
45.
Good morning, my name is Valeria and I'm from the MIFI University. My major is international scientific and technological cooperation, and the thing that I want to do in the future to facilitate this kind of cooperation to address global challenges. One of such challenges is air pollution. In this regard, we consider the cooperation between the CTBTO and the World Health Organization to be crucial to address air pollution and to achieve SDG 11. We think that this cooperation will help to alleviate the problem of air pollution through radionuclides monitoring, studying health risks, updating air quality guidelines, encouraging authorities to follow standards and regulations, and raising awareness. So, you are more than welcome to visit our poster. Thank you.
Thank you. 47.
Good morning. If you are interested to know about tsunami in Eastern Mediterranean and the only value to tsunami deposits evidence for a tsunami in Eastern Mediterranean, and in addition to that, the risk scenario for the old city of Alexandria and who will survive the next tsunami, please come and visit me. I'm in poster 47, near to the bar where is the coffee. So have your coffee and come and discuss with me. Thank you.
Great. So do we have number 4 or 27 now in the room? No. Then that's a good opportunity to catch up with coffee fast enough before everybody else, hopefully. So thank you very much for the amazing job. And
yeah, sorry, just so we will reconvene at 2:30. But for information, the 3 first presentations are still missing. So please come to the desk to provide your presentation. So the first one of amplifying the impact of CTBTO data, renewable energy and sustainable development is missing, and the last, the catastrophic failure of the iron ore tailings. So please come to the desk as soon as possible to provide your presentation. Thank you.
It's hard.